Hello, so today I'll be going over acetals as protecting groups. Just a quick review, if you have a ketone, for in this example it's acetone, and you react it under acidic or basic conditions with an alcohol like ROH, you can form a hemiacetal. We can track the carbons here. The original oxygen on the ketone, the same one on the alcohol group of the hemiacetal. You can then subject it to a second reaction only under acidic conditions and a second equivalent of ROH, and then you'll form your final product of an acetal. But acetals can also be cyclic, and they can be important protecting groups because it allows you to do selective reactions. Let's say we start off with the acetone again, and we react it under acidic conditions and a vicinal diol. We can then get a cyclic acetal shown, and this group right here is essentially the protecting group because the oxygens are no longer carbonyl oxygens, and instead they're ethers, so in some ways they can be protected that way. But I'll go over the mechanism. So let's say we start off with acetone, and we do it under acidic conditions, and we also have our vicinal diol. Now normally the vicinal diol will act as a carrier for the proton, but I'm just going to draw the abbreviated version of the acetone being protonated, and we get this charged molecule here, and this essentially makes the acetone ready for attack, because normally you would expect the oxygen to carry a negative charge, which makes the carbonyl carbon a positive charge, but with the proton and the cation, it makes this new intermediate an even better electrophile. And the vicinal diol being an alcohol, normally they aren't very good nucleophiles, but since the electrophile is so good, it'll undergo this reaction where it attacks the carbonyl carbon, and the pi electrons flip up to avoid pentavalency, and it'll form this tetrahedral compound. Let's see. And it'll also be charged. Now, to get rid of the hydrogen, we can come in with a conjugate base. If you're using something like HCl, Cl minus would do the trick, and you would end up with a neutral compound, and this would be your hemiacetal. Now from here, we want to make a hydronium leaving group, which is basically just water, and to do that, the alcohol group here grabs the proton, it's positively charged, and then it leaves. This gives us water, but then it also leaves behind a carbocation. This makes it the perfect place for the oxygen to attack, and this will form a cyclic molecule, but it's still charged, and it'll undergo one last step, because if the first step is protonation, the last step is deprotonation, the hydrogen will get attacked by the conjugate base, and the electrons will be flipped back, and you'll end up with a neutral cyclic acetal with the protecting group. Now, as to some examples as why they can be served as protecting groups is if you have the starting molecule here and you undergo this reduction. Normally, what you would expect is the ketone to form into a secondary alcohol and the carb acid to become a primary alcohol. However, if you first turn into a protecting group, you would get this compound. Let's see. And then remember, it only reacts with ketones, so the carb acid wouldn't be affected. But then once you go once you do, once you react it with LAH, since it's no longer a carbonyl oxygen, it will no longer be affected, and thus the carb acid will be the only thing that gets reduced. But the interesting thing is that there's also a quench step, and remember this whole reaction is reversible, so the protecting group comes off, and you're left with this, and plus water, but also your vicinal. Now, for some retrosynthesis, we have some examples here. Now, for the first one, you can recognize that it's a hemiacetal because of the alcohol group, but what you can do is you just draw a line right there, and that's where you know you can separate it. You want to redraw the molecule, and the alcohol group turns into aldehyde, and the ether turns into an alcohol, and then you keep stereochemistry. For these acetals, what you need to look for is the carbon that is attached to both oxygens. You draw like a disconnecting line, and you want to redraw the molecule. But instead, the carbon turns into a ketone, and the oxygens turn into alcohols. Similar to this other example, you want to find the carbon that is attached to both oxygen. You cut them here, and you get your final product. As this.